A warm welcome to the lecture on the subject of wavelets and multirate digital signal processing. We continue in this lecture to build upon the particular class of filter banks which we had introduced in the previous lecture, namely the conjugate quadrature filter bank. A number of issues related to that filter bank were left unanswered in the previous lecture. To some extent, our introduction of the filter bank seemed ad hoc at points. What I mean by that is, we had suddenly made little twists in the nature of the filters, where a proper justification had not been given simply because there was a bit of a chicken and egg problem. The justification was best seen after we went through the discussion, and that is what I had promised, that after we complete an understanding of this filter bank, many things will be a little more clear. So, let us embark then upon that filter bank once again. Let us look at that conjugate quadrature structure once again, first in toto and then in specifics. So, in today's theme, we shall look at conjugate quadrature filters in depth, and we shall again consider one specific class of those conjugate quadrature filter banks, namely the family of filter banks and family of multi-resolution analysis that emerge from Dobash filters. Incidentally, as I mentioned, Dobash, or sometimes it is pronounced as Dobashes, has been a mathematician, scientist, engineer, whatever you want to call her, of repute. Her important contribution in this field has been to propose a family of compactly supported wavelets, which also have some other interesting properties. It turns out that the Haar wavelet is the baby of the Dobash family, the simplest of the Dobash wavelets, and there are further and further ones, of which we shall give an introduction today. In fact, the central idea in the Dobash family is to build upon what we had briefly mentioned in the previous lecture, namely the idea of keeping and annihilating polynomials of higher and higher degree on one of the two branches of a filter bank. Anyway, we shall look at specifics as we go along, but this is to put the lecture in perspective. So, we shall talk today about the conjugate quadrature filter bank, and we shall look specifically at the Dobash family of MRA. Now, you see, the conjugate quadrature filter structure, as we understood it, had the following relationships between the filters. So, we had the analysis high pass filter was related to the analysis low pass filter by the following relationship. And we had promised that we shall understand this a little better today. Of course, the synthesis filters were related very easily to the analysis filters. So, you had G 0 Z being H 1 of minus Z and G 1 Z being minus H 0 of minus Z. This of course, was essentially Elias cancellation for you, these two conditions. But now, let us focus on this relationship of H 1 to H 0. So, first let us justify why it is a high pass filter. So, let us consider this expression z raised to the power minus d h 0 minus z inverse, and let us put z equal to e raised to the power j omega as we do to obtain a frequency response, whereupon we will have e raised to the power minus j omega d h 0 minus e raised to the power minus j omega. Now, if we take the magnitude of this, as is normally what we are interested in, we have the magnitude of e raised to the power minus j omega d h 0 e raised to the power minus j omega is the same as the magnitude of h 0 e raised to the power minus j omega. Well, minus, I am sorry, minus of this. That is because the magnitude of this is 1. And now, let us look at this quantity, the magnitude of h 0 minus e raised to the power minus j omega. You see, if h 0 is a filter with real coefficients. So, if h 0 z corresponds to a filter with a real impulse response, and that is the class in which we are most interested. In that case, h 0 e raised to the power minus j omega is going to be h 0 e raised to the power j omega complex conjugated. That follows in a straightforward way from some basic properties of the discrete time Fourier transform. What we are saying essentially is that the magnitude response of a filter with real impulse response is symmetric in omega and the phase is antisymmetric. Now, if we now replace e raised to the power minus j omega by minus e raised to the power minus j omega, what are we really doing? So, h 0 minus e raised to the power minus j omega is essentially h 0 e raised to the power minus j omega plus minus pi. We have done this before. We have noted that minus 1 is essentially e raised to the power plus minus j pi, and therefore, what we have done here is essentially to shift this by pi, either forward or backward, it does not make any difference, because there is a periodicity with a period of 2 pi. Anyway, what we do know is that a low pass filter, I think we have seen this quite frequently now, a low pass filter when shifted by pi on the frequency axis becomes a high pass filter, of course, a low pass filter aspiring to be a low pass filter with a cutoff of pi by 2. It becomes an aspirant for a high pass filter with a cutoff of pi by 2 again. And similarly, when a high pass filter is shifted by pi on the omega axis, it becomes a low pass aspirant with a cutoff of pi by 2. We have seen this pretty much before. Anyway, recognizing this, then we have an interpretation for what we just did. So, we said this minus essentially shifts by pi, and therefore, h 0 e raised to the power minus j omega without the minus sign would have been a low pass filter as it is, because of this conjugate symmetry that we have here. And now, with the introduction of a minus sign, it becomes a high pass filter. So, we have a convincing argument now that H 1 Z, the way we have constructed it. So, we have convinced ourselves, we have shown H 1 Z in the way that we have constructed it, namely Z raised to the power minus D, H 0 minus Z inverse is indeed high pass or a high pass aspirant. It aspires to be an ideal high pass filter with cutoff pi by 2, provided of course, H 0 Z is an aspirant to be a low pass filter with cutoff pi by 2. So, now things have fallen into place. The only issue is, why have we taken this peculiar expression? Not so peculiar really, now we do not see it as so peculiar, but why the Z inverse and so on. So, we will understand that in a minute. You see, I will just give you a trailer for the reason. The trailer is that this automatically brings a condition on the magnitude. We will see that shortly. Anyway, now let us put down the Elias cancellation condition is anyway put down. We need to put down the perfect reconstruction condition. So, let us put down the perfect reconstruction condition. We did that yesterday, but we will do it a little more carefully. The perfect reconstruction condition essentially says that you would have G 0 Z, H 0 Z plus G 1 Z, H 1 Z must be some constant, we called it C 0 times Z raised to the power minus D. And what are G 0, G 1, H 0, H 1 here? Now, we have agreed that G 0 Z is essentially H 1 of minus Z. So, we had H 1 minus Z, H 0 Z plus now G 1 Z we had agreed to make minus H 0 minus Z, and H 1 Z of course, we have agreed to make it Z raised to the power minus D and so on, but let me write H 1 Z for the moment, and we want this whole thing to be C 0 Z raised to the power minus D. Now, we will substitute H 1 Z in this equation, and we have minus 1 to the power D Z raised to the power minus D H 0 Z inverse times H 0 Z minus. Now, again you have H 0 minus Z here, and H 1 Z becomes Z raised to the power minus D H 0 minus Z inverse. This you desire should be C 0 Z raised to the power minus D. Now, you know, this Z raised to the power minus D that we have here, in fact, we should not quite have written it like this, though what we have written now happens to be correct. We should have started by giving a different value for the delay here and the delay on this side. But now, again through serendipity or through convenience, we can actually make them the same. The purpose of putting this Z raised to the power minus D here was actually to take care of this term here. So, it is not coincidental that we have written the same D on both sides, though that should not have been done initially, we are doing it right away to emphasize that this Z raised to the power minus D term that we introduced in H 1 was meant to take care of this. So, what we are saying in effect is that we want the rest of it to match as well. So, what we desire for perfect reconstruction is essentially this: minus 1 raised to the d H 0 z H 0 z inverse minus H 0 minus z H 0 minus z inverse is a constant. Now, again we have the freedom to choose the value of capital D here. Again, the main issue is whether capital D is odd or even. If capital D is odd, then we have a minus in both places for both the terms. If it is even, then this is a plus and this is a minus. Let us choose to make capital D odd. And in fact, again there is a reason for that, it is not arbitrary. You know, we have just looked at the Haar filter bank, where we have a filter of even length, a length 2 filter actually. All of them, 1 plus z inverse, 1 minus z inverse on both sides are of length 2. When we replace z by z inverse, so let us take the Haar case once again. You had H 0 z of the form 1 plus z inverse whatever, forget the by 2 here. In the Haar case, H 0 z inverse would have been 1 plus z, and the z to the power minus d H 0 z inverse, or if you choose, you can write minus z inverse as we do, and this would then become minus here z raised to the power minus d H 0 minus z inverse is actually intended to make this causal. This filter is non-causal. So, you need to introduce a z raised to the power minus 1 here to make this causal, and therefore, d becomes 1 in this case. So, you see the role of d. I had hinted at this yesterday. You see, we said that the reason why we cannot avoid a delay is because you want the filters to be causal. Now, you see what we mean. This z raised to the power minus d term has been put there to retain causality, and you just put as much of a d as is needed to allow for causality. And so, here the d required is 1. Now, in the Dobash family, we keep augmenting the filter length by 2 in every rung of the family ladder. So, when we go from the baby of the family, namely the Haar MRA, to the next member of the family, we augment the length by 2. So, we have a length of 4. When we go to a length 6, it gives us the third member, and so on, length 8 the fourth member, and so on and so forth. So, successive even lengths of filters give us successive members of the family in the Dobash family. Now, what we are going to do is slowly move towards building the second member of the Dobash family, and therefore, the next case would be capital D equal to 3. So, you would have a length of 4, and you would have a maximum power of z equal to 3, z cubed, when you write H 0 minus z inverse. So, that is the role of z raised to the power minus d here. All right. Therefore, it is justified for us to begin by assuming that d is odd. So, let me put that down once again for you. In this relationship that we have here, we shall now assume d to be odd. With d odd, we essentially have for perfect reconstruction H 0 z, H 0 z inverse plus H 0 minus z, H 0 minus z inverse is a constant. Let me explain. You see, when d is odd, then both of these are minus signs. So, you can take away the minus sign from the left hand side and put it on the right, and this is anyway a constant. So, negative of a constant is also a constant. So, there we are. Now, what does this mean? We need to reflect on it a little. We will first reflect on it in the frequency domain. So, when we put z equal to e raised to the power j omega, what do we have here? H 0 z, or rather H 0 e raised to the power j omega times H 0 e raised to the power minus j omega plus H 0 minus e raised to the power j omega, H 0 minus e raised to the power minus j omega is a constant. Now, once again we shall remove the minus sign here and shift omega by pi, and we shall also note that if you have a filter with a real impulse response, then H 0 e raised to the power minus j omega is essentially the complex conjugate of H 0 e raised to the power j omega. The same holds here. When you have omega replaced by minus omega here, you again get a complex conjugate of this. So, all in all, for real filters, we have H 0 e raised to the power j omega, H 0 e raised to the power j omega complex conjugate plus H 0 e raised to the power j omega plus pi plus minus, if you please, H 0 e raised to the power j omega plus minus pi complex conjugate is a constant. Now, we have a very beautiful conclusion here. You see, this is the magnitude squared and this is again a magnitude squared. So, there we are. What we are saying in effect is mod H 0 e raised to the power j omega squared plus mod H 0 e raised to the power j omega plus minus pi, the whole squared, is a constant. Now, this is very interesting. This is exactly one of the properties that we had introduced in the context of the Haar system, namely the property of what is called power complementarity. Here it is clear now that by this construction we have achieved power complementarity in the high pass and low pass filters of the analysis side, and in fact, it is a simple consequence that if we look at the synthesis side, they are also power complementary. In fact, I leave it to you as an exercise by using the relation between G 0, G 1 and H 0 to show that the synthesis side is also power complementary. So, what do we have here? It is very interesting. The analysis filters are power complementary. And so too the synthesis filters. So, as I said, exercise show this. We have already proved it more or less, it is just a little bit of, as they say, dotting your i's and crossing your t's. You need to write down neat proof, but I think that is a good thing to do. We must leave a couple of exercises for the class to do, and this is a very simple exercise with which we begin. Use the discussion that we have just had over the last couple of minutes to work out the details to show that the analysis filters and the synthesis filters are both a power complementary pair.